Hello everyone, this is part 4 video on past year NEET questions from the chapter thermal properties of matter in physics. Now those who are looking at this video, right, can also take a look at the previous 3 parts so that you will have continuity of questions. We'll start with a question that has come in the year 2002. This is a straightforward question based on the Stephen's constant. So they're asking us what is the unit of the Stephen's constant. Stephen's constant is also known as what? Stephen-Boltzmann constant. So if you look at the absolute radiation power of a black body, so the absolute radiation power of a black body will be equal to what? Sigma A T to the power of 4, where temperature must be on the Kelvin scale. Okay, so here they are just asking us what is the unit of this sigma, right? So power means what? SI unit is watt, is equal to sigma SI unit. That is what we are trying to find. Area, what is the SI unit? Meter square. Temperature is in Kelvin scale, so it will be Kelvin power 4. We are looking for the unit of sigma, means we have to bring the other terms to the left side. So what is it? Left side, what we'll have? Watt in the numerator. Denominator is what? Meter square into Kelvin power 4. That is what will be the SI unit of sigma. So what is the right answer for this? Option D is the right answer. Next we have a question based on the thermal conduction. Consider two rods of same length. Means what? Their length is same. So let us say L is the length. Both of them have the same length. And different specific heats, S1 and S2, means they are made up of two different materials. And conductivity is K1 and K2. Obviously when they are made up of two different materials means the thermal conductivity will be a property of the material type, right? So it will also be different. And area of cross section A1, A2, area of cross section is also different, and both having temperatures T1 and T2 at their ends. Means, if one end of the rod is maintained at T1, other is maintained at T2. That is same for both the rods. If the rate of loss of heat due to conduction, means that is the conduction power, so how much heat is going through that rods per given time, that is what we will call as the rate of loss of heat, is equal. So in both the cases it is equal, they are saying. Then we have to conclude the relation between the other parameters. So first what we'll do is we'll look at the situation that we have. So we have two rods. This is rod 1 and this is rod 2. So rod 1 length is same, rod 2 also length is same. Temperatures, both the ends are maintained at what? T1 and T2. This is having K1, this is having K2. Areas will be different. Now what is given is the rate of loss of heat through conduction. That is the conduction power is same in both of them. Means the dq by dt is same in both of them. So what is the formula for the conduction power? K into area of cross section into delta T, temperature difference between the ends, divided by the length. So K1 is the first, A1 into T1 minus T2 by L. For the second one, K2 into A2, temperature is same, right? So here we are assuming T1 is more than T2. So T1 minus T2 divided by L. Both are same, right? The rate of loss of heat is same in both of them, which means what? K1 into A1, T1 minus T2 by L, that is equal to what? K2 into A2, T1 minus T2 by L. So we'll see that T1 minus T2 is cancelled, L is also cancelled. So what do we have on the LHS? K1 A1 is equal to what? K2 A2. This is the relation. So what is the correct answer for this? Option A. We can see something interesting. Though they have given us the specific heats, they are not coming into picture. So specific heats will be related to what? When the material is absorbing heat, that is where we'll talk about the specific heat, right? But here since we are only talking about the conduction, the S1, S2 values will not even come into picture. Okay, so that is the kind of an information that they are giving us to mislead. So some of us will be trying to think over, okay, where these S1 and S2 will come, and we might even try to forcefully fit. Somehow we'll try to think about a vague idea and try to fit the S1 S2 into the solution. So that we should not be doing. So whatever the approach you follow means you will get correct answer. Even in some of the other chapters also we have seen at times they could just give us some information which is not required. We'll move on to the next question. This is the question that has come in the year 2002. This is based on the again radiation power. For a black body at temperature 727, its radiating power is 60 watt. and the temperature of surrounding is 227. Okay, if the temperature of the black body is changed to 1227 degrees Celsius, then its radiating power will be how much? See here, right? So we have the body. Its initial temperature is what? 727 degrees Celsius means we will require the values on Kelvin scale, no? So plus 273 means what? 1000. So we have the object at 1000 Kelvin. Surroundings is what? What is the surroundings temperature? It is 227 means if you add plus 273 it will be 500 Kelvin. Now while the object is radiating, the surrounding also will radiate. So surrounding radiation will be falling onto the object. So in this case, right, we have to consider the net radiation power, because whatever the heat that is radiated by the surrounding will be falling onto the object. So net radiation power means whatever the radiation that is given by the object, which is what given by the Stephen's law. So sigma A T power 4, and surrounding radiation is coming onto the object, means we have to subtract it. That is what? Sigma A T naught power 4. So whenever we look at the net radiation, right, it will be what? Sigma A T power 4 minus T naught power 4. So this is what is the relation for the net radiation power of any object. So whenever they talk about the surrounding temperature, right, we should keep one thing in mind clearly, that we should consider what? Net radiation power. Okay. So here the initial net radiation power is what? 60. When you change the black body temperature to 1227, they are asking what is the 1227 means what, by the way? In terms of Kelvin scale, what is it? 1500 Kelvin. So initially, what is it? 60 watt is equal to what? Sigma A into temperature is what? 1000 power 4 minus 500 power 4. Okay. The new radiation in the second case, let us say E dash is what? Sigma A. What is the new temperature of the body? 1500. So 1500 power 4 minus surrounding is not changing. So we will require this E dash value. That is what they are asking. So what we will do? We will just divide these two expressions. So what we can do? We will just divide both these expressions. So let us say the first expression we will call it as equation 1, and call the second expression as what? Equation 2. So let us take it as what? Equation 1, and let us take it as equation 2. So we will do equation 2 by equation 1 means what? Left hand side we will get E dash by 60. So units will keep it away for some time. So this sigma A sigma B will be cancelled. Numerator what will have? 1500 power 4, 500 power 4. Denominator 1000 power 4. So if we see 1500 can be written as what? 3 into 500. 1000 can be written as what? 2 into 500. Means numerator here we will get 500 power 4. Here also there is a 500. We can take it common. Here also we will have 500 power 4. So means what? If you take that 500 power 4 common and cancel it off, right? Numerator here we will have what? 3 power 4 minus 1 by 2 power 4 minus 1. 3 power 4 means what? 81. 81 minus 1 by 2 power 4 means what? This is 16. 16 minus 1. So 80 by 15. Here also we can cancel. What is it? 5 16s are 5 3s are, which means what? 16 by 3. So E dash will be equal to what? 16 into 60 by 3. So the 60 will go to the right side, numerator. So 3 1s are 3 20s are. What is 16 into 20 means? 320. Unit is what? Watt. So what is the radiation power in that second case? How much it is? 320 watt. So all that we are doing is here in this question, right? The only place where some of us could go wrong is not considering the net radiation power. So we have to consider the net radiation power. So whenever the surrounding temperature is given, means what? The object is radiating the heat to the surrounding. Surrounding also radiate back. So we have to consider the net radiation power. Next we have a theoretical question on the black body. Which of the following is the best close to an ideal black body? So what is an ideal black body? This is a thing that probably a lot of you would have seen in a regular class also. So there is nothing called as an ideal black body, because ideal black body is supposed to do what? It is supposed to absorb all heat falling on it. Means there will be no reflection. When the black body is absorbing the heat, it will only radiate. There will be no reflection from the black body. So here, one of the closest approximation is if you take any object with a very small opening. So this is the small opening or cavity. Okay. And when we allow the light or radiation to go through this small opening, right? So what could happen is, if you maintain the inside surface to be uneven, so inside also the surface must be what? Uneven. Then this whatever the radiation going in will undergo multiple reflections inside. On top of it, if you cover the inside surface with a black material, then it will be able to absorb the radiation better. So what will happen is, because of these multiple internal reflections, we will see that whatever the radiation going in will eventually get absorbed. And since the cavity is small, the chance of radiation coming out will be very minimal. So this is what we will consider as close to an ideal black body, and this will be maintained at a constant temperature. So when you look at it, right, the cavity inside an object, and of course the cavity also, we have to make sure that inside the cavity we have uneven surface and a material which will be able to absorb the heat better. So under these conditions, we can think of it like what? Black body, where it will only absorb whatever the radiation going in. Okay, so what we do is, outside, right, we will insulate it. Outside of this has to be insulated, so that there will be no heat loss. So this is what will be the idea of an approximate black body. So what is the answer for this? The cavity which is maintained at a constant temperature. Lamp black, right? Like say for example, if you have any lamp, you'll see after some time there will be a black color coating that is getting formed on it. It is nothing but the unburnt carbon particles. What is this lamp black? It is what? Unburnt carbon particles. That also will be able to absorb the radiation to a very great extent, but that will not be able to give the perfect situation of making sure that whatever the radiation is falling on it should not be reflected. Okay, so the closest approximation is what? It is the cavity which is maintained at a constant temperature. Of course, we have to consider all these other aspects also about the cavity. Okay. Next, we have another theoretical question based on the Wien's displacement law. Wien's displacement law expresses the relation between. So what is this Wien's displacement law? If you look at the radiation that is emitted by an object, the radiation will be emitted across a range of wavelengths. I mean, we can't even number them like lambda 1, lambda 2, because it will be continuous. So across a range of wavelengths, we will see that the radiation is going to be emitted. Now when we look at how much energy is coming through each of these wavelengths, so we look at what is the energy intensity coming through each of these radiations. That is what we'll typically measure by the quantity spectral energy density, means through each of these particular wavelengths. So we can see, if you look at between say for example, this is imagine 250 nanometer. So between 250 to 500 nanometer, we can see what is the amount of energy that is being emitted. So when you look at this spectral energy density graph with respect to the wavelength, we will see that at a particular value of wavelength, there will be a peak that will be reached. So what we will be able to see? We will be able to see a peak, and that peak, right, will correspond to what? It will be corresponding to the maximum energy emitted through that particular lambda. The peak will correspond to what? The maximum energy emitted through the particular lambda. So here we will have a relation. The relation is lambda m into T will be constant. That is what is the Wien's displacement law. So what is the Wien's displacement law? Lambda m into T will be what? Constant. Means what? If this lambda m is basically that particular lambda where we are getting the maximum energy being emitted. So that particular point, the spectral energy density will be what? Highest. So this constant is what is called as the Wien's constant B, We don't require the value here, but the value will be what? 2.898 into 10 power minus 3 meter into Kelvin. So this law, we'll see that even some numerical questions also can be asked on the Wien's displacement law. So what is it basically? It is the relation between what? The wavelength corresponding to the maximum energy and the temperature. So lambda m into T is what? A constant, which is what is called as the Wien's constant B. And what is the value of it? 2.898 into 10 power minus 3 meter into Kelvin. So we can quickly see one thing. As the temperature is increasing, right? The radiating object temperature is increasing, means the corresponding lambda maximum will be what? Decreasing. We can see from the graph also. So temperature is increasing means what? We can see the lambda m is shifting to the, so here the temperature is less. So lambda m is to the right side, higher value. As the temperature is increasing means we can see lambda m is shifting to the left. The corresponding maximum intensity lambda is what? Decreasing. Okay. Next we have a question which is based on the, again, the thermal conduction concept. A cylindrical rod having temperature T1 and T2 at its end. The rate of flow of heat is Q1 calories per second. This is the rate of flow of heat, means this is the rate of conduction. If all the linear dimensions are doubled, keeping the temperatures constant, then the rate of flow of heat is Q2. Means we have to tell the Q2 value in terms of Q1. So look at it. If you have a cylindrical rod, right? A cylinder will have a cross section area. What is the cross section area? Pi r square. Length of the rod is L, and temperature is maintained as what? T1 and T2. So initially what they are saying, the rate of flow of heat is Q1. Q1 is what? K, thermal conductivity of the material, into A into T1 minus T2 by L. What we are doing in the second case, all linear dimensions are doubled. Means what? L, if you say it is L dash, so L dash is what? 2L. Similarly, the radius of this area of cross section, R dash, will be equal to what? 2R. Now if R dash is 2R, means final area A dash is what? Pi into R dash square, right? Which is what? Pi into 2R the square, which is what? 4 times pi R square, which is 4A. So the new area of cross section is what? 4 times A. Now we look at Q2. Q2 is what? K into A dash. A dash means what? 4A into T1 minus T2 by L dash. L dash is mod 2L. So 2 ones are 2 2s are. So here clearly we can see, other than the 2, rest is what? Ka T1 minus T2 by L. That is what? Our Q1. So what is the relation we have? Q2 is equal to what? 2 times of Q1, which is option B. Like on this thermal conduction formula, right? We'll see that quite a lot of times they have asked questions mostly based on these scenario, like case 1, case 2. We'll have to relate the terms and then we'll be able to solve whatever they are asking. Next we have another question which is based on the Wien's displacement law. A black body has maximum wavelength lambda m. So whenever they say maximum wavelength, what is it? This is the wavelength corresponding to the maximum intensity of the radiation emitted. It's corresponding to what? Like the way we have seen in the previous discussion also, right? Like this one. This is what is our lambda m. Okay, this is the corresponding spectral intensity. Okay, so here lambda m at what? 2000 Kelvin. Its corresponding wavelength at 3000 Kelvin is. So remember what is it? So lambda m into T is equal to B, the Wien's constant, whose value is what? 2.898 into 10 power minus 3 meter into Kelvin. So here to solve this question we will not require this. So initially lambda m into initial temperature was 2000 is equal to, finally let us say it is lambda m dash, that is what we are supposed to find, into final temperature is what? 3000, right? So 1000 3s, 1000 2s, means what we'll have? We'll take the 3 to the left side, it will go to the denominator. So 2 times lambda m by 3 is what? Lambda m dash. That is what we are looking for. So what is the corresponding wavelength at 3000 Kelvin? We can see it will be what? 2 by 3 times lambda 1. It's what? Decreasing. 2 by 3 times means what? It is nearly 0.67 times lambda m, right? That's what we said, right? As the temperature of the body is increasing means the corresponding lambda m value will be decreasing. Next we have a question based on the calorimetry. This is a question that has come in the year 1999. If 1 gram of steam is mixed with 1 gram of ice, then the resultant temperature of the mixture is. So here, I mean, this is a sort of inadequate information question, but we'll go with some assumptions so that we'll be able to get an answer for this. So 1 gram of steam, we'll consider that this is at 100 degrees Celsius, and 1 gram of ice, we'll consider that this is at 0 degrees Celsius. So they should have mentioned what are the corresponding temperatures. Otherwise 1 gram of ice can exist in any temperature, right? So the temperature will play a role here. Now we basically mix both of them. What is going to happen? See, the ice is at 0. First the ice will melt, and then it will start increasing its temperature by absorbing the heat. What about the steam? Steam can get condensed, and then it can start coming down. So once it is condensed, it becomes what? Liquid water. It can decrease the temperature, but we have to see up to what extent they will come. For that, right, when we look at 1 gram of steam, when it is getting condensed, what is the latent heat of evaporation for water? It is 540 calorie per gram. This information also we have to remember, then only we can answer the question. Means when 1 gram of water is vaporized, we will require 540 calories we have to spend. When 1 gram of steam is getting condensed means what? It will give us 540 calories. Now look at the what is the energy requirement this side. Ice at 0, first we want to melt it. For that, what is the latent heat of latent heat of fusion for the ice? It is 80 calories per gram. Means, you know, we are melting 1 gram means we will require 80 calories. Now to take this, now we have water. To take this water from 0 to 100, because we have condensed the steam. The condensed steam is at what temperature? 100. It is giving us 540 calories. First step, to melt the ice, we require 80 calories. Now to take this water that is there from 0 to 100, the energy required will be what? Mass of the water, which is 1 gram. Specific heat capacity of the water, which is 1 calorie per gram per degree Celsius, into delta T is what? From 0 to 100 we want to take, means 100. So what we'll get? We'll get 100 calories. Means what? The total energy requirement is just 180 calories. So to melt the ice, which is at 0 degrees Celsius, and to increase the temperature of the water formed from 0 to 100, will require only how much? 180 calories. But by condensing 1 gram of steam, we will be getting 540 calories. So we will not be required to condense all the steam. The 1 gram steam will not be required for condensation. So what is going to happen? We are requiring only to bring this ice at 0 to water at 100. Will require how much energy? 180 calories is required, right? So for that, we would be needing only 1/3 gram of steam to get condensed. Because if 1/3 gram of the steam is condensed means how much energy we are going to get? 1/3 gram into 540 calories per gram, which is what? 180 calorie. And the remaining 2/3 will be in the steam form only. The remaining 2/3 gram will be in the steam. So what is the final mixture that we will be having? We will have the water that has come from the melting of ice. That is how much? 1 gram. Okay, so this is the final mixture that we will be having. And what is the final temperature? By the way, we got the answer, right? What is the final temperature? This is the answer. So what is it that we have? we have 1 gram of water at 100. This is come from the melting of the ice and bringing that water from 0 to 100. For this we have basically spent how much? 180 calories we have spent. And from the steam side, 1/3 gram is condensed. Means we have 1/3 gram in the form of water at 100. From this only we got this 180 calories. The remaining 2/3 gram is in the form of steam only, that is not condensed. So totally what do we have? 1 plus 1/3, 4/3 grams of water will be there at 100 and 2/3 grams of steam is there at 100. Okay, so what is the final temperature? They are asking only final temperature, right? What is the final temperature? It is 100 degrees Celsius. So whenever we have a question like this, right, especially with regard to the water, when they mention different states, so we'll have to look at on each side, because from the vapor side we will get the energy, on the ice side we will be requiring energy, so we'll have to see what is the energy required on one side and what is the energy we'll get from the other side, and then accordingly we have to step by step proceed. General thing is the amount of energy that we get from the condensation is going to be, condensation of the vapor is going to be significantly high in comparison to the energy required for the melting of the ice and even to increase the temperature of the water formed. Okay, so this is like a question where we have to make these assumptions. The initial assumption that we made is what? The steam is at 100 and the ice is at 0 degrees Celsius. Only with that assumption we are able to solve the question. Next we will go to another question. This is based on the radiation power again. The radiant energy from the sun incident normally at the surface of the earth is 20 kilocalories per meter square minute. So this is also by the way called as what? Solar constant. Okay, what would have been the radiant energy incident normally on the earth if the sun had a temperature twice that of the present one? See, there is a sun is radiating. Okay, it will radiate in all directions and it is part of it will come to the earth. So how much energy is falling on the earth will depend upon what is the radiation power at the sun. So we'll see the radiation power will be proportional to what? T power 4, where T is the temperature of the sun. So initially the energy reaching the earth is what? 20 kilocalories per meter square minute. If you double the temperature, if the sun had a temperature twice the present, means what? If the temperature is changed to 2T, then let us say the energy we are getting is some E dash. Initial energy is E and let us say the new energy is what? E dash. So look at it, what do we have? The E dash by initially what are we getting? 20 kilocalories per meter square minute. This is equal to what? 2T whole power 4 divided by T power 4, isn't it? Because the energy coming to the earth will depend upon what? Radiation power at the sun. Initial radiation power is what? Proportional T power 4. Final radiation power is what? Proportional to 2T power 4. So what is it? T power 4, T power 4 is cancelled. We'll have 2 power 4, which is what? 16. Means E dash value, we'll get the answer. So E dash will be equal to what? 20 kilocalories per meter square minute into 16. What is it? It will be 320. Unit will be same, kilocalories per meter square into minute. Okay. Next we have another question based on the radiation concept. A black body is at a temperature 500 Kelvin. It emits energy at a rate which is proportional to, straight Stephen's law question, right? So what is it? The radiation power emitted by the black body is equal to what? Sigma A T power 4. Means what? It is directly proportional to 4th power of the absolute temperature. We should take the temperature on the Kelvin scale or the absolute scale. Means what? It is proportional to 500 power 4. That's it. So what is the answer for this? Option B is the answer. So this is about the part 4 video and we'll see in the next part.